I welcome all of you to the class, and today we are going to discuss the last equation of our force and acceleration analysis, and after that we will be applying all the equations that we have derived or that we have tried to understand till now. I have been saying since the initiation of this force and acceleration chapter that as far as the question of force acceleration of a rigid body is concerned, the force and acceleration analysis, the force and acceleration analysis, that is finding the forces acting on the body and the acceleration of the rigid body, we actually deal with few equations, okay? And as far as those equations are concerned, the equations that we have, the first equation is summation of all the forces or resultant of all the forces acting on the body, say for example along x-axis, is equal to the mass of the rigid body and acceleration of the center of mass of the rigid body along x-axis, okay? Similarly, we have a summation of all the forces acting on the rigid body along y-axis is equal to the product of mass of the rigid body multiplied by the acceleration of the center of mass of the rigid body along y-axis. Same we talk about the z-axis, okay? Apart from that, we have summation of all the moments about the center of gravity of a rigid body is always equal to 0. This is what we have derived. These are the equations of the motion of a rigid body, okay? These equations we will be using, okay, in order to find out the acceleration and the nature of forces acting on the rigid body. Apart from this, we have also talked about, yesterday we were talking about the angular momentum of a rigid body, and we defined the angular momentum of a rigid body as an integral of r cross vdm. This is the definition of uh, this angular momentum we gave yesterday in the previous class. And we also said, as far as the time derivative of the angular momentum is concerned, the time derivative of angular momentum about any point is equal to the moments of the force about that very point. Okay, this is what we did in the previous classes. We'll be solving the questions, the numericals we'll be doing, which will be based on these formulas. But before that, today I want to actually take you to a very important equation, and today we'll be talking about a very important fundamental theorem of this kinetics. That's what we call as the moment of momentum theorem. Moment of momentum. I will consolidate on it. Moment of momentum, or what you call as the angular momentum of the rigid body. Angular momentum of a rigid body, okay? Angular momentum of a rigid body. So what do we mean by the moment of momentum or angular momentum? Let's suppose we have a rigid body. Let's suppose we have a rigid body. And let's call this rigid body as beta, in the way we have been calling the rigid body configuration by beta, okay? Let's select a point on the rigid body, and let's call that point as point Q. And let's say that this rigid body is having rotational motion, and the rotational motion of this rigid body is represented by the angular velocity, that is omega. Let's suppose we have a frame of reference, what we call as a ground frame of reference, okay? In this ground frame of reference, let's select a point, let's call that as point P, okay? From point P, let's draw a vector to point Q. From point P, let's draw a vector to point Q. This is the vector PQ. Now, let's try to draw, as far as this point Q is concerned, let's say this point Q is having velocity, and let's say its velocity is, say, for example, in some direction. Let's call this velocity as V. V is the velocity of Q. We call this as VQ. We call this as velocity of point Q, okay? Around this point Q, let's say we have a very, very small mass element, okay? We take a very small mass element around this point Q, and let's call that mass element as, let's say its mass is very small, we call this as dm. The radius vector we draw from P to Q, let's call this as the radius vector r, or we call this as radius vector r subscript P and Q, okay? Now, let's define the angular momentum of this rigid body beta with respect to the point P, okay? Therefore, we can write the angular momentum of the rigid body, h, we represent the angular momentum. The angular momentum of a rigid body about this point P in the ground frame of reference is defined as, is equal to integral of, this is the definition of the angular momentum, is equal to the integral of radius vector drawn from point P cross velocity of the point Q, that is VQ, multiplied by the mass of around the point, the mass around this this element, the mass around the point Q, that is dm. This gives us, once we take the integral, okay, this gives us the total angular momentum of this rigid body about point P. That's why we're writing this as angular momentum about point P. We also select our coordinate axis. Let's say this is our x-axis, and we suppose this to be our y-axis. Let's call this to be our y-axis. Okay, so this we state that this is our y-axis, and we say this is our x-axis. Okay, so as far as the z-axis is concerned, the z-axis will be perpendicular to both these axes. Okay, and it will be perpendicular to the plane of this screen. Okay, it will be perpendicular to the plane of the screen and coming outwards. Okay, so we can write this as, this is equal to, this angular momentum can be written as integral of, now look at this radius vector r. This radius vector r can be resolved into two components. It does have a component along x-axis. Let's call that as, its component along x-axis is x I cap, okay, and it does have a component along y-axis, okay, and let's call that as magnitude is y, and that component is along y-axis, that is yj cap. Okay, since this r vector lies on the xy plane, therefore we can write this as the components of r vector are, it is xi cap plus yj cap. These are the components of r, and we have the cross product with v. Now, as far as the velocity of q is concerned, velocity of q in terms of velocity of point P, we know from the kinematic definitions of the velocity, we know velocity of point Q is equal to velocity of point P. Velocity of point Q is equal to velocity of point P plus r drawn from P to Q, that is r cross omega. Okay, this is the definition of the kinematic definition of velocity between the two points. Okay. So this is how we have been writing the velocity vector drawn between the two points. Okay. So as far as the point Q is concerned, we are representing the velocity of point Q in terms of the velocity of the point P. Okay, that is, I need to make a little correction here. It is omega cross r. Little correction is here. This is omega angular velocity, omega cross r. Okay, this is how we write it. Now, as far as the point P is concerned, okay, let me write the velocity of q in terms of P. I will write this as velocity of P, though in most of the in your book the velocity of P has been selected to be equal to 0 in most of the cases, and it states that P is a point at rest, but P may be a point at rest or may not be a point at rest. Let's not make it a special case by saying Vp is equal to 0. Let's generalize it. Let's say the velocity of point P is Vp. Okay, if we somehow, if I okay, let's write this as velocity of point P. We write this as Vp. Okay, plus omega cross r. That's it. Fine. Now, in order to, we will rub this up. Now, as far as the point P is concerned, let me consider for some time to make this equation a bit handy and easy to understand. Let me suppose P is certainly a point which is at rest. That is, let's say the velocity of point P is equal to 0. In next case, we will not say that velocity of point P is equal to 0. Even if you are given that the velocity of point P is not equal to 0, then you can still use this equation. Now let me suppose here for some time Vp is equal to 0, point P is at rest. Therefore, the expression will become integral of xi plus yj cap, I mean to say. And its cross product with, it is to be crossed with omega. As far as the omega is concerned, it is the angular velocity of the rigid body, okay, or the angular velocity of the vector PQ. Okay, if you curl your fingers in the direction of this arrow, the thumb will go along the z-axis. Okay, it will be perpendicular to the board and coming out of it. Okay, that's the direction of our z-axis. So I can write this as omega vector is equal to omega k cap. Okay, cross product with r vector, and I know the r vector we are writing as in terms of its components as xi cap plus yj cap. This is fine. Okay, and I have in product of dm, okay, the dm here. So I will write here this is dm. Okay, this can further be written as this is equal to integral of, okay, I will write this as this is xi cap plus yj cap cross product with, okay, this is omega into x, that is omega x. Then we have k cross I is equal to j cap. I will write this as j cap. Then I have uh, omega multiplied by y, that is omega y. And we have k cross j. K cross j is minus I, so it will be minus I cap. This is fine. Okay, and we have dm. We'll go a step ahead. Therefore, this becomes integral of, this is x into x, that's x square, multiplied by omega, that is omega x square. This is omega x square, omega x square. This is I cross j. I cross j is equal to, I cross j is equal to, I cross j is equal to k cap. Okay, I cross j is equal to k cap. So I will write this as, this is k cap. This is one expression. Then we have I and I cross I, that is 0. So I will directly take this y, j with j will be, j cross j is 0. So j will be with this I cap, will be crossed with this omega y I cap, that is omega y square. Okay, and we have this j cross I is equal to plus k. Okay, so that is plus k cap, and we have dm out of it. Okay, so we can write this expression again as, we can further write this expression as, let me grab it. This expression can still be written as, we are writing as angular moment of the rigid body about point P is equal to, we can write this as, this is integral of omega x square dm plus integral of omega y square dm. Okay, this is the expression that we are getting from this equation. As we go ahead, I need to define this x square dm. Since omega is the angular velocity and I assume the angular velocity to be constant, therefore this will come out of the integration. I will have integral of x square dm plus integral of omega integral of y square dm. Okay, if we recall from the moment of inertia, when we are talking about the area moment of inertia of a rigid body, sorry, moment of inertia of a plane area. Okay, when we were talking the moment of inertia of a plane area, at that time we had a plane area. Okay, this was an area for us. This was our x-axis. We were treating this to be our x-axis, and this we were treating to be as y-axis. We suppose this to be our origin. Okay, we were selecting a small area element here. We were saying let the area of this element be dA. Okay, let this area element be at a distance x from the y-axis and be at a distance y from the x-axis. Then we were saying the moment of inertia of this area about x-axis is equal to the moment of inertia of this total area about x-axis was coming out equal to integral of y square dA. This was the definition of moment of inertia about x-axis. Okay, this is that inertia we call as moment of inertia of an area. Okay, or we also call this as second moment of an area. This is called the second moment of an area. Now look at the definition of the area, look at the moment of inertia, area moment of inertia, compare these formulas. Similarly, we are talking about the moment of inertia about y-axis is equal to integral of x square dA. Okay, now compare these two expressions. Compare these two expressions with the expressions under integral signs here. Okay, so you can see that the variable is same. You have integral x square, you have integral x square here. You have integral y square, you have integral y square on there as well. So it means except for dm here, you are having dA here. Okay, this you call as, this is called the area moment of inertia, and this term we call as the mass moment of inertia. Okay, in mechanics this is called the mass moment of inertia. So we define the angular momentum about point P of the rigid body becomes equal to omega, and we write this as, this is I x square Iy, we write this as, this is mass moment of inertia about y axis. Okay, plus omega, okay, y square, this is mass moment of inertia about x axis. Okay, this becomes the expression for the, this becomes the expression for the angular momentum of a rigid body. Okay, say for example, now the rigid body motion is such, the rigid body is restricted to move only along x-axis or y-axis. Okay, if the rigid body is having the motion only along x-axis, if it's moving only along x-axis, okay, we can still say that the total moment of inertia is equal to, or we can write this as, this is, I can still write this as Ix plus Iy multiplied by omega. Okay, this is equal, the way we have been defining the polar moment of inertia when we are talking about the mass moment of inertia. Okay, the sum of moment of inertia about x-axis and y-axis is equal to the moment of inertia about z-axis. This is called Iz omega. That is equal to the, that's equal to the angular momentum. So we write, for a rigid body, as far as the angular momentum is concerned, HP is concerned, angular momentum about any point is concerned, that's equal to moment of inertia about the z-axis multiplied by its angular velocity. Okay, we know why we are dealing with these equations. If I wind up all these equations that we have now in hand, the equations that I have in hand are like summation of all the forces, or resultant of all the forces, resultant of all the forces along x-axis is equal to the product of mass of the rigid body multiplied by the acceleration of center of mass along x-axis. Okay, summation of all the forces along y-axis is equal to the product of mass and acceleration of the center of mass along y-axis. Summation of all the forces along z-axis is equal to the product of mass and acceleration of the center of mass along z-axis. This is one. Number two is the equations that we have about the, because the rigid body motion, planar motion of the rigid body is translational as well as rotation. These are the translational equations of motion. Like the examples I am giving you of the motion of a eraser on a blackboard or on a whiteboard. The motion of the eraser is essentially a planar motion. Okay, so if you look at the motion of the duster, okay, it's the motion on a plane, but essentially it does have rotational motion, it has translational motion. These components, these equations give us the translational equations of motion. What about the rotational equations of motion? I know that summation of all the moments, summation, the resultant of all the moments about any point P is equal to integral of r cross mv. This is what we have in, sorry, r cross f, r cross f, this equation we have been using. And summation of all the moments about the center of gravity is equal to 0. In fact, this is the radius vector drawn from point P to the center of gravity. I will write this is rpg cross f. Okay, and we have the angular momentum of the rigid body is equal to integral of r cross VDM. This is one more equation. We have, apart from this, we have angular momentum H is equal to I times omega. I is the moment of inertia about the perpendicular or the z-axis, omega is the angular velocity. We also have the time derivative of the angular velocity about any point P is equal to the summation of all the moments about that very point P. Okay, these are the different equations that define the motion of a rigid body in plane. These all equations are to be taken into consideration while we talk about the motion of the rigid body in plane. Let me apply all these equations now. Okay, So as we apply all these equations, what we are going to do is, let's take a problem from the book. If we look at the problem from the book, like this fundamental problem we have, it says that we have a uniform rod. Before I go ahead, I need to, yes, there is one more important thing before solving these problems. Like we said, H is equal to I into omega. Okay. In order to make use of this equation, we should know the moment of inertia of the rigid bodies. Okay. We should know how to calculate the moment of inertia of this rigid body. Before we solve these problems, we should actually know how to make use of, how to find the moment of inertia of the rigid bodies. Okay. That's what I had left while I was starting this chapter. I told you that we will not start with the definition of moment of inertia, but this moment of inertia will come somewhere in the equation while we'll be trying to make use of it. Okay. This is why, that's why the chapter has been started with the concept of moment of inertia, I. So I will return back to the initial page of the chapter to give the definitions of the moment of inertia. Okay, that's here. So I will return back to make you understand how do we find the moment of inertia, though the way we have calculated the moment of inertia, area moment of inertia, in the same way we'll be calculating the what we call as the mass moment of inertia. Okay, so let's talk about, this is the moment of inertia. This is where the definition of moment of inertia has been provided. The moment of inertia, the moment of inertia of any mass, of any rigid body, the moment of inertia of any rigid body about an axis like z axis is equal, take a small mass element at a distance r. Okay, moment of inertia about any axis is defined as integral of r square dm. Okay, let me show you how to make use of this equation. Say for example, we have an x-axis. Let's suppose we have an x-axis. Let's treat this to be our y-axis. Okay, let's suppose there is a rod. Let's suppose we have a rod of length L. Let's suppose we have a rod of length L. The length of this rod is, say for example, L. Okay, its length is L. Its area of cross section is negligible as compared to its length. Okay, now this rod total length is L, and its two endpoints lie at x is equal to 0. One end of the rod is at x is equal to 0. Another end of the rod is at x is equal to L. This is our x-axis and this is our y-axis. If we are asked to calculate the moment of inertia of this rod about y-axis, okay, so what we will do, we will take a small area element, let's take a small area element, very small area element, take a small area element, such that this small area element is having a very small thickness. Let's say its length is very small, not thickness but length. Its length is very small. Let's call this length as dx, and let's suppose that this area element is at a distance x from the y-axis. Okay, it's at a distance x. Okay, therefore using the definition of the we know the moment of inertia about y-axis is given as integral of the distance from, I will write it like this. I will write the definition first, integral r square dm. Okay, r is what? R is the distance of the element. R is the distance of the element from the axis about which we have to find the moment of inertia. And for us, our r is equal to x. Okay, so we'll write this as x square dm. Dm is the mass of this element. Okay, now look, when this small element whose thickness is dx, it has a very small mass. Let's call that as dm. Okay, when the length of the element is L, when the length of the rod is L, at that time its total mass is m. When the length of the element will be 1 unit, at that time its mass will be m by L. Now when the length is dx, therefore the mass of the length dx will be equal to dm, that will be equal to m by L multiplied by dx by unitary method. When the total length is L, mass is m. When length is 1 unit, therefore mass will be m by L. Therefore, when length is 1 unit, mass is m by L. When length is dx, therefore mass will be m by L into dx. So we can write this is m by L into dx is the mass of what? Is the mass of the small element having length dx. Therefore, we will write the moment of inertia Iy becomes equal to integral of x square dm, and in place of dm we will write our m by L, and we have dx. Okay, now if you look at x is the variable of integration. The value of x goes from x is equal to 0 to x is equal to L. Therefore the limit of integration is from x is equal to 0 to x is equal to L. I will solve it here. Therefore the moment of inertia about y-axis becomes, the moment of inertia about y-axis becomes, m is constant, L is constant, it will come out of integration, it will be m by L. And then we have integral of x square dx. Okay, that will be x cube by 3. I will directly write here, it will be x cube by 3. Okay, and the limit of integration goes from 0 to L. Okay, that is moment of inertia about y-axis becomes equal to m L cube by 3L. That will become m L square by 3. This is m L square by 3 is the moment of inertia. ml square by 3 is the moment of inertia of the rod about y-axis. Okay, so let me show you. So if we have a rod, of any area of cross section, okay, and if its total mass is, if the mass of this rod is m and the length of this mass is, say for example L, then the moment of inertia about this axis, okay, is equal to I, which is given as m L square by 3. This is the moment of inertia of the, rod. Okay, in the same way we have, say for example we have a cylinder as is given here. Like for example we have a cylinder like this. We have a cylinder. What is the moment of inertia of the cylinder about the z-axis? We have to solve it. Okay, similarly we have a cone. Okay, similarly we have a sphere. We have to find the moment of inertia of sphere, of cone, of different things about the given axis. So we have now somehow we could reach to the equation h is equal to I omega, and we are defining now the value of, we are calculating the, we are understanding how to find the value of this moment of inertia. Number 3 is, if you look at this h is equal to I omega, this is an equation of a rigid body. It's a rotational equation of motion of a rigid body. If you compare with the translational equation, F is equal to mass into momentum. This is angular momentum. That is, if you compare it with linear momentum is equal to mass into velocity. Linear momentum is equal to mass into linear velocity. Angular momentum is equal to moment of inertia multiplied by angular velocity. So that's why it is sometimes said in mechanics, in rotational motion, the mass moment of inertia has the same significance as the significance of mass in linear motion of the rigid body. So what significance the mass has in linear kinematics or linear kinetics of the rigid body, the same is the significance of the mass moment of inertia in the rotational kinetics of the rigid body. So in the next class, we'll be talking about more about how to find the value of I for different solids. And then after finding the value of I for different solids, we'll try to solve a few more problems. And with that, we'll end the force acceleration analysis. Thank you very much.